Hello everyone, I am Mahalakshmi, Assistant Professor in Physics from Hindustan College of Engineering and Technology. In this audio, we are going to discuss a few topics under properties of matter, that is regarding beams, the definition for a beam and the bending moment of a beam. The objective of this audio is to discuss about the beams, bending moment of beams and the expression for the bending moment of beams. We know that elasticity is a property of solid materials which return to their original shape and size after the forces deforming them have been removed. Examples are shock absorbers of vehicles, natural rubber, metallic wire and stainless steel. Now let us discuss a beam, which is also an elastic material. What is a beam? A beam is a horizontal structural member used to support horizontal loads such as floors, roofs and decks. Types of beam loads: uniform, varied by length, single point and combination. Figure shows the examples of a beam. The bending action of a beam, that is when a force is applied, the beam undergoes sagging. The sagging action of a beam about the neutral axis is depicted in this figure. Now let us see what is bending moment. Definition of bending moment. A bending moment is the measure of the internal stress that is produced by the external force or the moment causing the element to bend. And pure bending, it's a curvature. Sections originally perpendicular to the axis of the member remain plane and perpendicular. Plane sections always remain plane, and the sign convention for bending is: for positive bending moment, beam bends towards positive y direction, and negative bending moment, the beam bends towards negative y direction. And the figure shows the beam that is loaded. Because of this load applied, the beam bends, and this figure is here is an example for the bending moment when this load is applied. Beams. A beam is defined as a rod or bar, circular or rectangular, of uniform cross section whose length is very much greater than its other dimensions, such as breadth and thickness. It's commonly used in the construction of bridges to support roofs of the buildings, etc. Since the length of the beam is much greater than its other dimensions, the shearing stresses are very small. Let us see the assumptions of beams. While studying about the bending of beams, the following assumptions have to be made. Number 1. The length of the beam should be large compared to the other dimensions. And the load, that is the forces applied, should be large compared to the weight of the beam. Point number 3. The cross section of the beam remains constant, and hence the geometrical moment of inertia Ig also remains constant. Number 4. The shearing stresses are negligible. And number 5. Curvature of the beam is very small. Bending of a beam and neutral axis. Let's consider a beam of uniform rectangular cross section as shown in figure. A beam may be assumed to consist of number of parallel longitudinal metallic fibers placed one over the other, and they are called filaments. And this is the filaments which is shown here of a beam. Let the beam be subjected to deforming forces at its ends as shown in the figure. So we are applying forces at the ends. So these forces changes the shape and size of the beam. So these forces are called deforming forces. Due to the deforming force, the beam bends. We know the beam consists of many filaments like this. And let us consider a filament. This is a filament AB at the beam. It's found that the filaments lying below AB gets compressed. Therefore, the filaments, that is the layer which AB which remains unaltered, is taken as the reference axis or neutral axis, and the plane is called the neutral plane. The deformation of any filaments can be measured with reference to the neutral axis. So we conclude that all the filaments above AB gets elongated and all the filaments below AB gets compressed, and the filament AB, which remains unaltered in length, is taken as the reference axis, otherwise called neutral axis. Let us consider a beam under the action of deforming forces. The beam bends to the circular arc. Let AB be the neutral axis of the beam. Here the filaments AB above AB are elongated and the filament below AB are compressed, and the filament AB remains unchanged. So let PQ be the chosen arc from the neutral axis. If R is the radius of curvature of the neutral axis and theta is the angle subtended by it, at its center of curvature C, we have the arc length PQ is equal to arc theta. We can write the original length P prime Q prime is equal to R plus X into theta. We can calculate the extended length. So we must consider at a distance x from the neutral axis. You can write the extended length as increase in length is equal to P prime Q prime minus PQ, which is equal to R plus X into theta minus R theta, which is equal to X theta. So linear strain is equal to X theta by R theta is equal to X by R. We know linear strain is equal to increase in length divided by original length. We know the Young's modulus Y of the material is equal to normal stress divided by linear strain, or cross multiplying normal stress is equal to linear strain into Young's modulus Y. If delta A is the area of cross section of the filament P prime Q prime, then the tensile force on the area delta A is given by substituting 4 in 5, we have tensile force is equal to normal stress into area. So tensile force is equal to Yx by R into delta A. We know that moment of force is equal to product of force into perpendicular distance delta A. So moment of tensile force about the neutral axis AB is equal to PQ is equal to Yx by R into delta A into X. So PQ is also written as Y by R into delta A into X squared. The moment of force acting on both the upper and lower halves of the neutral axis can be got by summing all the moments of tensile and compressive forces about the neutral axis. Therefore, the moment of all the forces about the neutral axis is equal to Y by R into delta X squared into summation X squared into delta A. Here Ig is equal to summation X squared delta A is equal to AK squared, which is called the geometric moment of inertia, where A is the total area of the beam and K is the radius of gyration. Therefore, total moment of all the forces or internal bending moment, which is equal to Yig by R. And let us now discuss a few special cases for rectangular cross section and for circular cross section. So for a rectangular cross sectional beam, if B is the breadth of the beam and D is the thickness, then area is equal to breadth into thickness. So B into D, and radius of gyration K is calculated to be equal to D squared by 12. Therefore, Ig equal to AK squared, which is equal to BD into D squared by 12, which is equal to BD cube by 12. Substituting the value of Ig in equation 6, we can write bending moment for a beam of rectangular cross section is equal to BD cube divided by 12R. And number 2, the special case is circular cross section of a beam. If B is the breadth and D is the thickness of the beam, then for a circular cross section, if small r is the radius, then area capital A, which is equal to pi r squared, and K squared is equal to r squared by 4. This is the value of radius of gyration for a circular beam of cross section. We have Ig is equal to AK square, which is equal to pi r square into r squared by 4 is equal to pi r power 4 by 4. Substituting the value of Ig in equation 6, we can write the bending moment for a circular beam of cross section is equal to pi y r power 4 divided by 4r. Thank you all. Thank you for your patient listening.